Thank you. So for my third lecture, I want to change direction a bit and tell you about another perspective on states of matter and quantum field theory that we call entanglement bootstrap. And I'm particularly excited to talk about it because I think it has some very nice resonances with the perspective that Horacio has been telling us about. And I'd really like to understand how to reconcile these points of view. I decided to use slides today partly because I want to show some numerical data, partly to spare you my handwriting, and also partly to make sure that I get to the good stuff, which I think, yeah. Okay, so let me tell you what entanglement bootstrap is. It's a bit abstract. It requires a little bit of motivation. So I guess maybe the best thing to call it is sort of a research program. And the guiding idea of this research program is the following thing, which I call central dogma, which is the following statement. And I'm going to spend a lot of time explaining this statement. So the statement is the following belief, which is the statement that all the universal properties of a state of matter are encoded in the reduced density matrix of a ball of a single representative state. Okay, so there's a lot of words. Let me try to explain. So first, let me say what I mean by first let me say what I mean by universal. So the situation I have in mind is there's some lattice or otherwise well-regulated model, and everything I want to talk about involves local systems. The degrees of freedom are spread over space, and ideally a tensor product over space at the shortest distances. And the ball I'm talking about is not too small, not too big. Okay, so what I mean by universal, this is a maybe somewhat restrictive definition of the word universal. What I mean is property of a normalization group fixed point. Okay, so and therefore a property of its whole basin of attraction. Right, so all of the theories that flow to this fixed point have the same value of these properties. That's what I mean by a universal property. And by representative, I mean some point in that basin of attraction of the RG fixed point. Okay, that's what I mean by the word representative here. Okay, good. And this is a slightly restrictive definition of universal because I'm excluding universal crossovers. So say a scalar field with a small mass is something that I don't want to talk about. That's a description of a crossover from the massless scalar field in the UV to nothing in the infrared, which is difficult for what I want to say, though some people could reasonably call that universal. Okay, so yeah, let me explain what I mean by the phrase central dogma. So this term is borrowed from the molecular biologists, and what I mean by it is that it's a sort of question-generating idea, right? It's sort of a thing that generates questions for the research program. And for the molecular biologists, it was this idea that DNA makes RNA makes proteins, and specifically, so part of that is the idea that every cell in a living organism contains the complete instructions for making the whole organism. and so I think I'm happy about that similarity because that's sort of the idea here, that each small region, each local region of a many-body state contains the complete instructions for finding all of the universal data. So I think it's a good name. That's what I mean by central dogma. Okay, so now I'd like to spend a few minutes telling you why we believe the central dogma. And it'll give me some opportunity to review some of the tools that we'll use all the time for the rest of the lecture. And I have to warn everybody about the nature of the statements I'm about to make. The things I'm saying are the kinds of statements that mathematical physicists I think would very much like to prove under some assumptions. Right? So the crucial question is, what are the assumptions under which these statements are true? I don't know what those are exactly. What I mean by the following statements is that they're usually true. Definitely an adversarial, the proverbial computer scientist who wasn't here yesterday could definitely find exceptions to each of the statements that I'm going to make. Okay, so the first point is that the reduced density matrix of the ball knows whether the state we're talking about is the ground state of a local Hamiltonian. So that's one property of the state that we might want to know. And the way we can tell is that the entanglement entropy of the reduced density matrix of the ball will satisfy an area law if it's the ground state of a local Hamiltonian. Roughly because the local Hamiltonian demands that nearby degrees of freedom are entangled with each other and not directly with very distant degrees of freedom. Okay, and therefore when we make an entanglement cut, the information we lose is dominated by the region near the boundary. Of course, there are some very important exceptions to the statement. There are ground states of local Hamiltonians whose entanglement entropy grows more quickly than the area of the region, some of which will be very important below. But roughly, this is the expectation. Okay, so we can tell whether it's the ground state of a local Hamiltonian, which is the situation that I'll care about. Okay, secondly, we can tell whether the local Hamiltonian has a gap or not. The idea being that within this ball, we can pick 2 points, say some point here and some point here, and compute a correlation function of the local operators inside this region. So that's something that we can do. That's something we can do just using the reduced density matrix, right? This correlation function in the state that we're interested in. If x and y are points inside the ball, we can compute just using the reduced density matrix of the ball. And if that correlation function decays exponentially, if we can see some exponential decay as we move the points apart inside the ball. Well, right. So this is why I don't want to talk about say a light scalar. Okay. Yeah. Right. Well, so well, I think the crucial question is the size of the ball compared to the correlation length, right? So if the ball is bigger than the correlation length, then you can see the exponential decay. Yeah. Right. Yeah, that's true. Yes. Yes. Yeah. This is a true statement. Yes, I agree. But this is exactly the reason that I wanted to exclude a light light scalar. Okay. Yes, please. Yes, that's the goal. Yes, that's right. So despite the fact that we often, when we talk about topological order, we often talk about what's the ground state degeneracy on the torus, a crucial point that I want to make is that all of that information is visible just in the reduced density matrix of the ball. Yeah, great. Okay, so we can tell whether it's gapped or gapless, at least if it's a fixed point, right? So then the correlation length is either infinity or close to the lattice scale. Okay. Now let's start to talk about more refined information. So in a ground state with liquid topological order, liquid means not fractons. In the case when the region is okay, let's talk about two spatial dimensions. If a ball in 2 dimensions is a disk, we've already heard several times that the entanglement entropy of the ball has an area law contribution, which is non-universal in the sense that it depends on this epsilon, which is say some UV cutoff. And minus the topological entanglement entropy, the TEE, which is related to this total quantum dimension of the anion. So that's one piece of anion data. Certainly, if it's 0, we know that there's no topological order, and so that's at least a way to a yes or no question: is there topological order? Okay, the list of reasons to believe it is pretty long. Bear with me. Okay, so that an exception to this statement about that the ground state of a local Hamiltonian has an area law, very famously, is the ground state of a 1 + 1 dimensional conformal field theory, where instead the entanglement entropy of a 1-dimensional ball, namely an interval, has this logarithmic dependence on the size of the ball, whereas the area law would be independent of the size of the ball since the boundary is just 2 points. And the coefficient of this area law is the central charge, right? So this universal piece of data about the fixed point, which is the first thing we want to know about a 1 + 1 dimensional CFT, and measures how many degrees of freedom it has. Oh, of course. I mean, the log of epsilon is, yeah, you can shift by changing the cutoff. Yes. Yes. Of course, there's also an area law contribution. Yes, that's right. Yes, of course. Yes. But we can, of course, we can extract this by studying the dependence on the size. Yeah. But nevertheless, we can extract this universal piece by studying the dependence on the size. Okay. And I'd like to emphasize that there's a similar formula, a related formula, in higher dimensions for the case of CFT in more than 1 + 1 dimensions, in the case when the ball is round, right? So every ball in 1 + 1 dimensions is round, but in higher dimensions this is a further restriction. And in the case where the ball is round, we know a formula for the entanglement entropy, and in particular, we can extract the analog of C, which is also, very importantly, an RG monotone. Okay. Good. So far, all of the pieces of evidence I've described, most of the pieces of evidence I've described just involve the entropy, right? The entropy is just one piece of information in the reduced density matrix, right? It's in fact a very small fraction of the information in the reduced density matrix, which is actually an operator. And one way to think about that operator, rho sub x, where x is the same as b, is to take its logarithm. Why am I doing this? Well, I'm doing this so that rho looks like a Gibbs state, right? It looks like e to the minus beta h, where beta we can arbitrarily set to 1, and this so-called entanglement Hamiltonian is the thing that we'll think about. And there are lots of things we can do with this operator. One thing that Shinsei already talked about is this modular commutator, which is obtained in the following way. So take our ball or some part of it and divide it up into 3 parts that meet at a point. And let's think about the entanglement Hamiltonian of AB, so that's this part, and the entanglement Hamiltonian of BC, that's this part. And their operators, we can take their commutator, and then we can take their expectation value in the state. And some virtues of this quantity, some properties of this quantity, are that it's, first of all, odd under parity. If I do a parity transformation, I reverse the roles of A, B, and BC, and so the commutator is odd. So it's odd under parity. It's additive under stacking. So that is, if I take a state and tensor it with another state, this J of that combination of states is the sum of the J's. And then finally, under an assumption that I'll explain in a little bit, it can be shown to be independent of smooth deformations of the shape. So here it doesn't matter that the assumptions that I'm talking about basically are the assumption that the state is some liquid topological ordered ground state. And in that case, it's independent of the shape of the region. We can deform it arbitrarily. And so these 3 facts are evidence that make it plausible that this quantity is related to the chiral central charge. Why does it have to be what? Have to be chiral. It is chiral. I don't know why it has to be. I mean, yeah. If the state is invariant under time reversal, it's 0. Yeah. Well, essentially the answer is because it's pure imaginary. Yeah. That's why we need to put a factor of I here. I'm making it real by putting this factor of I. Yeah. 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 Well, no, parity you can see, right? Because under a parity transformation, you flip this picture over. So A, B, and C are in some particular cyclic order here, and under a parity transformation, that order is reversed. Yeah. It's just geometric property. Yes, exactly. If you wanna. The ball is not in a pure state. Yeah, I'm assuming that, in fact, yeah, if the ball is a pure state, it's 0. Yes. Psi is the big wave function. I should have, ideally, if my Beamer skills were better, I would have drawn this lattice extending over the whole slide, and the ball is just some part of it, right? So the whole thing is a pure state, and so the reduced density matrix of the ball is definitely a mixed state, yeah. Unless the whole thing is a product, in which case it's the whole thing. It's boring. If the ball is in a pure state, this vanishes. Yes, that's right. I don't think I can remember how to show that right now. You mean like a free theory of a massless scalar?
Yeah, for example.
Well, okay. I guess that example is time reversal invariant, so it's 0. Yeah, 0. Yeah, but more generally, you could ask about gapless theories. So here, I was. This assumption here is very much assuming that the state is. I'm going to explain that. Yeah. No, it's a very good steak sauce. Very good steak. Yeah, it's an assumption that I'm going to explain, which encapsulate. It's part of the idea that it's liquid topological order. Yeah, this is a teleological reference that I used just to fit it on the slide. Okay, and relatedly, so this is sort of a special case of a bigger picture, which is this bulk boundary correspondence that Shinsei talked about quite a bit, which I guess generally, I don't know, part of it is attributed to Lee and Haldane, who first conjectured that in a chiral liquid topological state, the spectrum of the reduced density matrix, the spectrum of the entanglement Hamiltonian, is the spectrum of the edge theory. All right, so that's another piece of evidence that the universal data is present in the reduced density matrix of the ball. Okay. All right, so now this slide is a digression, a small digression, and the purpose of the digression is to persuade you that this dogma that for which I'm giving evidence is actually a broader principle than just a statement about ground states. So far I've only talked about ground states, but here's a more general statement. So the eigenstate thermalization hypothesis is our best understanding of why statistical mechanics, quantum statistical mechanics works. And it's the following statement. It's the statement that, it's actually a very strong statement, that if we have a single finite energy density eigenstate, E, of a local Hamiltonian, so this is a state somewhere in the middle of the spectrum, right? Finite energy density, very different from the ground state. It has volume law entanglement. Just using the reduced density matrix of a ball in that state, in fact, the ball can be as big as half the system, as big as half the system, and actually it doesn't have to be a ball. We can reconstruct the Hamiltonian, the whole Hamiltonian. So I said that the principle is that we can extract all the universal information, but this is actually a much stronger statement. If we know the Hamiltonian, obviously we know in principle we know all the information, right? Because we can do whatever we want with the Hamiltonian. It's a lot more information than just the universal information. Yes, Fiona. Oh, yeah, good. This is, interacting. Okay, yeah, okay. Interacting enough, let's say it that way. Yeah. Generic, let's say that. Yeah. No, you can make there are some exceptions. Yeah, integrable, you can violate this. Yes, that's right. Yeah, but of course, there's a reason that quantum statistical mechanics has been used for 100 years, and MBL is something that people talk about now. Yeah. Right, it may not exist. I don't want to, register an opinion about that. Okay, but I think it doesn't. Okay. And so here, this picture is some very beautiful evidence of this statement. So the statement is, let me say the statement. The statement is that the reduced density matrix of the region A, so where A is any region, any subsystem less than half the system size, is a thermal state, is a Gibbs state, where the entanglement Hamiltonian just is the Hamiltonian of the region A. So it's very important that it's local. You have to do something at the boundary, but the That's right. That's right. Usually, so the microcanonical statement is you take some window of energies. It's a single state. Yes, it's a very powerful statement. And here's some evidence for it. So this is in some spin chain, non-integrable spin chain. And this is a list of the eigenvectors of the thermal state at some temperature beta. I didn't say what beta is. You have to figure out what beta is to get the energy right, right? The state is specified by some energy, and that determines beta. Yes. Yes. Oh. Oh, but that's I mean, that's a very special Hamiltonian, right? The terms all commute. Yes. Yeah. This interacting. Yeah. Yeah. So, but maybe when I think when you say phase, you mean the ground state phase, right? The zero temperature phase. Yeah. Yeah, but here I'm talking about a different kind of phase, right? I'm talking about the finite energy density situation, right? So I feel like it's finite temperature, right? It's what happens to the system at finite temperature. Yeah. That's right, exactly. It's the statement that the state provides its own path, and you can definitely violate it by choosing too special a Hamiltonian. Yeah, yeah. It's a very strong statement. Yeah. It is. No, the sense of the usual, so often, I guess the way Srednicki initially stated it was a statement about correlation functions of local operators. But actually, so the point that Garrison and Grover made is that actually it's true even for operators as large as half the system size. Yeah. Yes, please. Yes. Yes. Yeah, I think people often use that word, and in fact, in the attempts to understand this why this is true, I think that word is quite useful. Yes. Yes, that's right. That's right. And so, no, that's absolutely correct. But here's some very nice numerical evidence for that statement. Yes, please. Okay. Yeah. So by HA, I mean. So I'm assuming that the Hamiltonian is local, so it's a sum of local terms, and HA is, well, in the interior of A, it's just the same sum of local terms, with some boundary conditions that I don't know. I'm not specifying them. Could be. So that's exactly the comparison that's being made here. Yes. 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 You can adjust at the boundary. That's right. Yeah, but what I'm saying is that you cannot adjust. You understand the difference? So you take the global thermal state with the temperature that you want, and then reduce the region. Yes, yes. The density matrix is the same as taking the A state reduced. That's what's actually being tested here. So that's exactly the comparison. Very precise statement and doesn't automatically fixes the boundary condition. Yes, that's correct. That's correct. It's not an assumption. I think it follows from the statement. Yeah, that's right. Sure. Yeah. So like I said at the beginning of this discussion, I'm making a set of statements that are usually true. Yeah. Yes, that's right. Which is a very weak assumption, right? The generic Hamiltonian is not integrable. Yeah. So, but let me just explain this picture. So exactly as Horacio said, so on this axis, we list the eigenvectors of the actual thermal state reduced to A, and on this axis, we list the eigenvectors of the reduced density matrix of the pure state at finite energy density at the corresponding temperature, and you see and this is just the overlaps of those wave function for, I think it was something like 16. The whole thing is 16 sites, and the region A is 5 sites. So and the overlap is very good. Okay, so this is a digression, but I want to just try to convey that this principle is actually very general. Okay, here we go. So So a consequence of this principle is that we should be able to tell from the reduced density matrix of the ball which kind of state we're talking about. Is it a ground state of a liquid topological order? Is it a state in the middle of the spectrum of some finite energy density region? And there should be some local conditions on that reduced density matrix that tell us which class of states it falls into. Yeah, so, okay. I'd like to be able to distinguish between these things by some condition that all CFT ground states satisfy. And once we identify the right such conditions, so the first goal of the program is to identify the right such conditions for each class of states. We can use them in two ways, each of which I think can be referred to as a bootstrap. The first way is we could take those conditions as axioms and then try to prove structural properties of the universal information that follow from those axioms. Right? The second thing we can do is just look for states that satisfy these axioms just in the space of density matrix of the ball. And so without any further input, we can identify states in the class that we're looking for. Okay, so the goal of the entanglement bootstrap program is to try to understand the structure of the universal information, right? What is the universal information for each class of states, and learn to get it out of the local reduced density matrix. All right, okay, this is one way to describe the goal. And there's a very important circumstance that I need to emphasize. The receptacle of the universal information, at least in most examples, is a low energy quantum field theory. Right? So in the case of liquid topological order, we expect that the low energy quantum field theory is a topological field theory. And so since we're constraining states, Hamiltonians whose low energy theory can be governed by such a field theory, we're constraining the field theory. Right? So in this way, the program teaches us something about quantum field theory. Okay. So here's the plan. I want to talk about the attempts to implement this program in three classes of states. The first one is liquid topological order in various in 2+1 dimensions and higher dimensions. And then for those of you who don't care about this subject, though I think that some of you do, we'll move on to attempts to extend the program to gapless states, to 1+1 dimensional conformal field theory, and then to conformal field theory in any dimension. Okay, so I should emphasize that there are a few other cases to which this program has been applied. So here I'm talking about liquid topological order in the bulk, so no boundaries. It's possible to include both gapped boundaries for states that allow gapped boundaries or gapped domain walls, and also to understand something about chiral topological states. So liquid topological order that doesn't admit a gapped boundary. And actually, there's quite a bit to say about that, which I mostly won't say. Yes, please.
So usually you see that emergent phenomena can be related to the infrared limit of your theory and the fixed point of the energy. And here somehow you're relating some ultraviolet properties with the infrared. So you're connecting the two
Yes.
limits of the theory. So that's the statement that sometimes you can do that.
Indeed. So the whole business is so we're starting with some well-defined thing, right? And to make it well-defined, necessarily we need to add some extra garbage in the ultraviolet, right? Okay, maybe these folks can directly define it without doing that, but the way that we are making everything well-defined is by embedding it into a finite dimensional Hilbert space, right? And that comes with some extra garbage compared to the information that we're trying to extract. And on the other hand, the universal information is in there, and the goal is to figure out how to get it out. Yeah, Fiona. There's an interesting question of how big the ball has to be.
So priori it has to be larger than the correlation length of your theory.
That's right. But like I said, that's right. But like I said, the information that I'm trying to extract is properties of a fixed point. Right, so there are two kinds of fixed points. There are fixed points whose correlation length is 0, and fixed points whose correlation length is infinity. and so in the latter case, of course, the ball won't be bigger than the correlation length. Nevertheless, we can learn from it. Yeah. Okay. So that's the exciting fact, the exciting part of items 2 and 3 here. Yeah. well, I think the picture you should have in mind is we're going to take a big enough ball that we can chop it up in various ways. Yeah. So the whole business will be chopping up the ball in various ways. So it has to be big enough that we can do that. Okay. Good. Well, that depends very much on which class of states we're talking about. So in the ETH for that case, certainly volume law entanglement would be one of the properties we'd want to impose. But actually, in all of the other cases, it's definitely sub-volume law. So in this case, it's definitely we want it to be area law. Oops. Yeah, in this case, we definitely want it to be area law. In this case, there's log violation of the area law. And in this case, it's area law also. In higher dimensional CFD, it's area law. Okay, but the area law is it's not a great condition to impose. It's a little hard to learn from just that assumption, right? And so the goal is to find more powerful assumptions, hopefully not too much stronger, which encode the kind of state that we want. Okay, and so in the case of liquid topological order, oh, I already said this. Okay, in the case of liquid topological order, yeah, by which I mean, by topological order I mean they're anyons. They're anyons, like I said yesterday, and meaning that there are excitations that are created, local excitations that are not created by any local operator. In higher dimensions by anyons, I include also, say, string excitations, that kind of thing. And by liquid I mean it's not a fracton theory. And so in this circumstance, we expect that the low energy theory is governed by a topological field theory, which, yeah, I guess I should say, topological field theory is it's like a trademark of the mathematicians, right? It's a thing. Mathematicians came up with some axioms for topological field theory for their own reasons, and there's a very reasonable conjecture that this definition that the mathematicians made is the right notion to describe the low energy physics of liquid topological order. But I want to emphasize that that's a conjecture, and that's something that a conjecture about which we can say something from this point of view. Okay, so what are the right conditions, if I give you the reduced density matrix of a ball, to tell whether it's a liquid topological order ground state, part of a liquid topological order ground state? And that question was answered very beautifully by these folks, by Bowen Shi, Kotaro Kato, and Isaac Kim. And the conditions are the following. There are two conditions involving only entanglement entropies, which we should impose on every region with the topology of a ball. Every region with the topology of a ball divided into its interior and its boundary, and a ball divided into its interior and its boundary cut in half in this way. And it's just a condition on the entropies. So maybe the simplest thing is to tell you what delta BCD is. It's the quantity that appears in the weak monotonicity inequality. It's a statement that's equivalent to strong subadditivity by a purification move. It's the statement that this combination of entropies is always positive. And A1, the axiom that I referred to earlier, is the condition that this combination actually is zero. So weak monotonicity is saturated for this topology. And the other condition, I'm going to explain some intuition about these two conditions. The other condition is actually delta BC is just the case of delta BCD where D is empty. So if you just ignore D here, you get this quantity, so that it's a statement about the boundary is just one part. So we'd like to impose these two conditions on any disk of we could just say small disks with the right topology. And a remarkable property of these two assumptions is that assuming them for small disks, you can prove them for larger disks. So they're sort of self-reproducing. And so if I assume them for large disks, in fact, they're true for every region of every decomposition of a ball into these two combinations. So let me give you some intuition for. Because of a gap, because of an area law, because of the universal nature of the subleading term in the area law. So in fact, yeah, these properties follow from this. Yes. So let me give some intuition for So in particular, they imply the area law. So let me explain how they imply the area law. So A0 by itself, this condition here, immediately implies the area law for round balls, right? So think about the case of A0 where B is a thin shell, right? I said it should be true for every region that topologically looks like this. So then the fact that this combination vanishes says that the entropy of the interior of the shell, which is most of the ball, is this difference. But then SBC is positive, so it's bounded above by SB, which is the thickened boundary. Okay, so it implies an area for round balls. And then using A1, you can show that it's true for every region with a subleading term that's independent of the shape of the region. Okay, so now that's the sense in which it implies this strong form of the area law, strong in the sense that the subleading term is topological. It's independent of the shape of the region. But these conditions are they're quite strong, as you can see, because A0 implies that if I take any region A, let's say A is some region over here, it implies that the mutual information between A and C, the interior of this ball, is exactly 0. Well, it's a little stronger than that, right? It's really that you're at the fixed point where the gap is infinity, right? Because it says that it says the correlation length is bounded by the thickness of B, right? a little trickier, yes. Okay, so this is the argument for that statement, which maybe I'll skip. And so this is it's really a statement not just that the state is a representative of a gap phase, but really that it's the fixed point. It's the zero correlation length fixed point. And A1, by the same set of maneuvers, implies that the conditional mutual information between A, any region outside, and C, conditioned on B, this buffer region, vanishes. So that is that the reduced density matrix of ABC is a Markov chain. Okay, so that's just. So the vanishing of the conditional mutual information is the definition of quantum Markov chain, and the reason for the name is that, so what's a Markov chain? It means that a Markov chain is a probability distribution on several variables where the marginals, right? So the distribution on A and B and the distribution on B and C determine the distribution on ABC. And this is a good name because that property is shared by a reduced density matrix, which is a quantum Markov chain. That is, so in general, if I give you a density matrix on AB and a density matrix on BC, which agree on B, the question of whether or not there even exists a density matrix rho ABC with those marginals is a very difficult one. It's like hard with a capital H, according to the computer scientists. But if you know that the state is a Markov chain, if you know that it satisfies this vanishing conditional mutual information, there's a canonical map by which you can reconstruct the density matrix rho ABC from. That's one application of the idea, but the idea, the crucial piece of information about the word Markov means that there's no memory, right? It means that knowing this part and knowing this part, you know the whole thing. There's nothing else to know. Yeah. So then that property is shared. Okay, and so this this Petz reconstruction map, which is the thing, by which we reconstruct the whole density matrix from its marginals in the case when it's a quantum Markov chain, is sort of the big engine of progress in this part of the story. Okay, good. So this follows just from A0 by this argument. So here's the idea. So suppose let A twiddle be everything in the world besides B and C. Then the fact that delta BC is 0, so delta BC is this combination, but by purity of the whole state, I can replace this with SA twiddle, and this is the conditional mutual information between A twiddle and C. But then strong subadditivity bounds that below by, if I trace out part of A twiddle and keep only some region A that's a subsystem of the whole rest of the world, I get back the mutual information. Say again? Great. So certainly a product state satisfies these conditions.
The first one doesn't mean there's a massive scalar you have the first one. So you have zero mutual information. But the second one is the one that is telling you something more, right? But the first one is just gap, very, very large gap.
It's not just that. Another thing it excludes, for example, is cat states. So a symmetry break, a state that breaks a global symmetry, like all up plus all down, will violate A0 as well. But your intuition is correct. It's saying that the correlation length is infinite, is 0. Yeah. So the role of the second one really is to allow us to deform the regions. It's because, well, okay, the idea is, here, let me just draw a picture. I'm not going to explain this in any detail, but the idea is, suppose I have some region. That's right, so A0 imposes clustering. Yes, that's correct. Yes, I think that's a good summary of what A0 does. That's right. Yeah, so here's what A1 does. Suppose we have the reduced density matrix of some region, which is part of the larger state. Then I can draw an A1 region here. So think of this as B, C, D. And then using the fact that, using this Markov property of C conditioned on B given, C, the fact that C, B, and any other A is Markov, I can reconstruct this density matrix. So that's the idea. It allows us to extend our density matrices. It allows us to do things like, suppose I have the density matrix here, and independently I have the density matrix here. It allows me to reconstruct the whole thing. It allows me to merge regions. Okay, so those are the basic tools. And okay, so I already emphasized this. These conditions are really too strong. They're not properties of an arbitrary representative. They're properties of the zero correlation length fixed point sitting here. However, exactly by the nature of the RG, suppose instead I'm sitting here, right? I'm sitting at some finite correlation length point, which eventually flows to this zero correlation length fixed point in the phase of interest. What that means is A0 and A1 will be violated if I study very small regions. And then as I consider larger and larger regions, the violation of A0, because of the fact that we're approaching this zero correlation fixed point that satisfies these axioms, the violation of A0 and A1 will decay as I consider larger and larger regions. And so by a coarse graining step or few, starting from an arbitrary representative, we can arrive at a state that satisfies this. That's the idea. Though of course, one would like to have a version of the story where instead I assume that I assume approximate versions of the axioms. Namely, suppose I have some upper bound on these deltas. We'd like to be able to prove that the statements that we'll make are true up to some errors controlled by that upper bound. That's something that people are working on. Okay, so I want to spend a few minutes talking about. Well, okay, so it's definitely topological. Holographic. I don't think that's true. I mean, is it true of the Torah code? I don't think that's true. Let me describe how we extract the universal information using these assumptions, and I think this will answer your question. Okay. Let me explain how we use these assumptions, and you'll see that the result is what you expect from topological states. we're not making any assumption about a bulk boundary correspondence here. It's not, there's no such input. Yeah, so this, I've described the two assumptions that we're making. It's a consequence. It's a consequence of these assumptions. Yeah. Okay, so let me describe it briefly. I want to try to be brief here because I really want to get to the CFT stuff. How one uses these axioms to learn something about the state. A very important concept to encapsulate this universal information is called information convex set. It's a slightly slippery concept. It's the following thing. It's a machine. I won't say functor, but it's a machine that takes as input a region which is part of our ball. So say, for example, suppose our ball is, I don't know, somewhere is like the whole upper left of the board, upper right of the board, and the region I'm going to think about as the annulus X here. It takes as input some state satisfying the axioms and a region in the ball, and the output is a set of density matrices, a convex set. Since if you add two density matrices, if you take a convex combination of density matrices, you get another density matrix. And it's the set of density matrices that locally inside our region X agree with the reference state, agree with the given state. So on each of these little disks that are covering my region X, a density matrix in the information convex set is the same as the reference state that we're given. However, this doesn't mean that globally on the region rho it agrees with the density matrix. It agrees with the given state because, for example, we can take the reference state that we're given, which we want to think of as the ground state, and act on it with this operator that creates an anion here and an anion here, connected by a string that necessarily passes through our annulus that we're thinking about. And now this string can be deformed. It can be moved around. So it doesn't change the state on any one of these balls, but it definitely changes the global state of the annulus. Okay. So that's the idea. The idea is we want to think about the density matrices that locally are the ground state, but globally there can be arbitrary excitations elsewhere. Okay. The axioms imply that this information convex set, this convex set of density matrices, is a topological invariant. It's a topological invariant in two senses. You get the same answer for under deformations of the shape of the region, and you get the same answer if you deform the state within the phase. And so by the same, I mean it's the same as a set, and moreover the entropy differences and the fidelity of these density matrices is preserved by these operations. Okay, and so the idea is that the structure of this convex set for various choices of the region X encodes this universal information. And okay, so what is a convex set? I mean, basically there are two possibilities. If our local Hilbert space is finite dimensional, it's a finite dimensional convex set. And there are two kinds of convex set. It could be like a simplex, where the extreme points are isolated. Right? So in order to make an arbitrary state in here, I just need to know about these farthest away points. And the other possibility is it could be like the block ball, right? The set of density matrices on a qubit, right? On a set of density matrices on a pure Hilbert space. Okay, now, so here's a fact. The information convex set of the annulus is always a simplex. The extreme points are isolated and orthogonal, and we can associate those extreme points, there's a finite number of them, with the anion types. And the picture you should have in mind is just this picture, that the extreme point associated with anion A is obtained by acting with this string operator that creates anion A inside the hole. The quantum dimension of anion A you can compute from the entanglement entropy of that associated density matrix. Rho 1 is the reduced density matrix of the reference state. So in the case of this annulus, the information convex set looks like this. But in the case of a two-hole disk, the information convex set actually is a collection of block balls. That is, it contains quantum information. The difference between these two cases is that in this case, the extreme points are labeled by classical information that can be copied. So in this annulus, actually, the interior part of the annulus knows which state it is, and so does the exterior part. The fact that you can copy the information means that it's classical. In this case, however, there's no way to divide this region up into two copies of the two-hole annulus such that each of them knows the information. That's some evidence that it can contain quantum information. And what is that quantum information? Well, if I specify the states on the annuli of the thickened boundaries to be ABC, this is the space of density matrices on a Hilbert space whose dimension we interpret as the fusion dimension of fusing anyons A and B to get C. And these two definitions of the quantum dimension and the fusion dimension are compatible with the usual relation between them. And then, okay, and I guess I'm not going to explain this, but we can also, from these assumptions, derive the statement that the entanglement entropy of the ball is area law minus a universal term, which is the total quantum dimension where these D's are the ones whose sum of squares appears there. Yeah. Metric on the space of density matrices. It's a convex set, right? So the information here, the really crucial information is what are the extreme points, right? A convex set is specified by its extreme points, right? Any state in the interior can be made by taking a convex combination of the extreme points. It's a set of... Yes. Yeah. Okay, good. And so very briefly, so the summary of the story, which I'm going to truncate the story now, there's a lot more to say, is that much of the structure of topological field theory, in particular modular tensor categories in 2+1 dimensions, can be extracted from this starting point. In particular, we know how to extract this list of anion types, their quantum dimensions, their fusion rules. We know how to show that there's a non-degenerate S matrix, so that is we can show that this modularity property is a theorem of entanglement bootstrap. It's sort of an assumption of topological field theory. I guess, yeah, this is this condition that the non-local operators always come in pairs. I mean, that you guys find. And a story I could have told, but it's a little complicated, is that you can extract the generalized symmetry operators from this assumption. Okay. The same axioms work in any dimension. In higher dimensions, the idea is you draw the same picture, but then study the volume of rotation about some axis. So we take a ball in higher dimensions and divide it up into its interior and its boundary. In higher dimensions, I would say that the correct framework for what the low energy all of the universal low energy information of a liquid topological order state is much less clear. I think it's much less clear that the mathematician's definition of TQFT is the correct one. Though maybe after what Horacio said yesterday, the mathematician's pessimistic statements that everything is a gauge theory, is a discrete gauge theory, maybe seems more plausible. I don't know. But that statement, there's a certain tension with the fact that in 3 spatial dimensions, so in 2 spatial dimensions, basically the only regions are the annulus, the 2-hole disk, the disk with n holes, right? Those are the only regions to consider. But in higher dimensions, there's this enormous multiplicity of open 3 manifolds whose information convex set we can consider. And a given such 3 manifold, its extreme points are associated with a certain class of topological excitations that are sort of fit in the holes, right? And so there's actually an enormous multiplicity of different types of topological excitations that can braid with each other in interesting ways. And this pessimistic, okay, I call it pessimistic, the statement that all TQFTs in 3+1 dimensions are Dijkgraaf-Witten theories implies that there's an enormous amount of redundancy in that information. There's an enormous set of relations between these things, which it seems very surprising to me. If it's true, I think there's something to learn about 3 manifolds from this, yeah.
Maybe you can reduce it by local operations. You can break the nodes so that you can bring it at the end to the ones that are kind of, let's say, trivial.
Maybe.
The ring, the surface.
Maybe, but think about, I mean, we can choose the region to be the complement of an arbitrary knot or link, right?
That doesn't matter because they are commutant of each other. So the complementary regions doesn't have anything because they
say nodes.
Yeah.
You have a knot and you can, no, he's saying the complementary of
The complement of a knot. The information convex set of the complement of a knot is a very non-trivial thing.
It's
Yeah.
all the information is already in the knot because of the commutant that's we can do that later. That's more clear.
The knot is an abelian group, then the other is an abelian.
Okay, I'd like to talk about this more, but I mean, knot theory is pretty non-trivial, and this construction produces invariance of knots. And so if there's really only a small set of theories, it implies relations among those invariants. Yeah.
Include knot theory in a local field theory that will have constraints that will basically do that.
In any given theory, of course, yeah, there are relations, yeah, but it implies that there's, okay, yeah, let's talk about it later. Yeah, good. Okay, so one important thing I should mention as a sort of disclaimer is for states with ungappable boundaries, there's an interesting, provable interesting tension between the following three statements. So, okay, I guess I mean a specific case of ungappable boundaries, namely ones with C minus non-zero. It's not possible to simultaneously have non-zero C minus in the form of the modular commutator, exact A1, and a finite dimensional local Hilbert space, a tensor product of finite dimensional local Hilbert spaces. So when I apply the theory I'm just describing to chiral states, to states with C minus non-zero, I always have to, there's always some violation of A1, at least at small length scales. The idea is that the infinite correlation length the zero correlation length fixed point necessarily has an infinite dimensional local Hilbert space. So one way to think about what I'm doing in that case is that I'm just taking the local Hilbert space to be infinite dimensional. This is a great question. Yeah, actually, we understand a little bit about that now. There's a correct statement that which in the limit where the correlation length goes to 0, it reduces to A1. That we figured it out actually by thinking about the kind of corner contribution that Shinsei was talking about. But that's a long story that I don't want to get into. Yeah. Okay. All right. So good. So that's what I wanted to say about liquid topological order. Maybe you believe me that this sort of strategy of imposing axioms on the reduced density matrix and using it to learn something is a good idea. One thing I didn't talk about in this case is that we could use this strategy also to search for topological order states in small Hilbert spaces. That's something that we're planning to do. Okay. Let's talk about CFT. So if you don't like topological phases, you can wake up now. I'm going to talk about CFT. Good. Oh, everybody loves CFT. Come on. What is the statement if a man who's tired of group theory is tired of life? It's a similar. I would say make a similar statement about CFT. Yeah. Okay. All right, so I emphasized already that if this central dogma is true, there must be some local conditions that tell us which kind of state we have in our hands. And so let's ask, what is the condition for the ground state of the 1+1 dimensional CFT? Okay, so I already said that in this case, the area law is violated logarithmically. I don't know a condition only involving entropies, which specifies that our state is a CFT. But in fact, in the case of the ground state of a 1+1 dimensional conformal field theory, we know quite a bit more about the reduced density matrix. Actually, for the case of a single interval, we know the form of the entanglement Hamiltonian itself. Okay, so this is really quite a lot of information in the continuum. Oh, maybe I should make a comment now. So here I'm writing a formula, which I learned from Cardy and Tony, for the entanglement Hamiltonian in the ground state of a field theory in the continuum, right? So there are people who will say that the von Neumann algebra associated with the field theory in the continuum is a type 3, and that means that we're not allowed to talk about the reduced density matrix, that it doesn't exist. And so what people mean when they say that in a type 3 von Neumann algebra the reduced density matrix doesn't exist is that it depends on the cutoff. Here, so I'm making a statement in the continuum which is a bit dangerous. Okay, so I'm gonna say some risky things in this slide in that sense, and I will pay for them in the next slide. It's a true. This is a true statement, and I'll pay for them in the next slide, but then I'll fix it. I promise I'll fix it. Okay, so let me explain this formula. This formula is true I guess maybe a way to say it that's easy to say is it follows from the Biesignaga-Wickman theorem, right? The Biesignaga-Wickman theorem is a statement about in relativistic quantum field theory, the entanglement Hamiltonian of a half space is just the Rindler, is just the boost operator, right? It's the operator that rotates us in Euclidean time. And so in particular, it's of the form integral over the half space of x times the energy density of the field theory itself. And so in particular, it knows about the Hamiltonian density. And in the so that's for any relativistic field theory. But in the special case of a conformal field theory, that half space is related by a conformal transformation to a round ball. And a round ball, in the case of 1 plus 1 dimensional CFT, is just an interval. And that x, the function multiplying the Hamiltonian density on the half space, turns into this function beta A here, this which we call coolness function, because it's like the beta appearing in the Gibbs state, and it's this function, right? So it vanishes everywhere outside of the interval. It's continuous, and it's just a quadratic function inside the region. Okay, and so the entanglement Hamiltonian is this known function times the Hamiltonian density of the conformal field theory, T plus T bar, plus a term that's just a C number, right? A term which if you take the expectation value, gives you the entanglement entropy. Okay, so my amazing student David Lin made the following observation. If we can think of these functions we get to pick x1 and x2, the endpoints of this interval. We can think of these functions as a basis of functions on the line, right? In fact, we can make any function by adding together combinations of these little locally quadratic functions. And in particular, a function that we can make out of them is 0. And so here's the idea. Choose 3 contiguous intervals, A, B, C, whose endpoints are specified by these x1 through x4. Eta is the cross ratio, the conformal cross ratio of those endpoints. And the statement is that this linear combination of those functions, so beta of a region is this function, which specified by the endpoints of the region. Everyone depends on x, I just didn't write them because it didn't fit in the line. This linear combination of functions is just exactly 0 for any choice of ABC. You believe me? And it's a statement about adding together these quadratic functions, right? So really there's only 3 coefficients you have to check: the constant term, the linear term, and the quadratic term. And so this is a picture of those functions for, this is beta A, this is beta AB. Maybe you believe me. You can check. Okay, so what is the consequence of that? Well, if you believe me that the entanglement Hamiltonian really makes sense in the continuum, it means that if we add together the same linear combination of k's, then when I plug in this formula, the thing that happens is that the coefficients of h of x, the coefficient of h of x for each point x, is just exactly 0. And so the only thing that's left is the C number part, and those C number parts add up, so this is like log of the length of A. When we add up those logs, the thing we get is this combination of the cross ratios where h of eta is just this binary entropy function of the cross ratio. As if the cross ratio were a probability. I don't know. I do not know why, how to interpret it as a probability. Okay, so this is an equation that, oh, yes, please. Was there a question? No, okay. Eta is this conformal cross ratio of the 4 endpoints of ABC. Yeah. So for example, if you take the whole thing to be so I described this on the line, but we could do the whole thing just on the circle. For example, if we divide the circle up into 4 equal parts, then eta is just a half. That's correct. Yeah, it's true for arbitrary relativistic CFT. But the part where I use conformal invariance is to map the half space to a ball. Yes. Was there another question? Yes. So by a conformal transformation, we mapped the half line to a finite interval. And so one of the, so the origin of the half line maps to x1, and the point at infinity maps to x2.
There is a part of it that cancels itself if you put so if you take KAB plus KBC minus the intersection minus the unit, it cancels itself.
Minus the, so yeah, indeed. So this,
You can take away some part of this expression and it's the same, right? It is also zero. No, but perhaps you need this. But no, I mean in the usual strong subadditivity of two intervals.
you're saying that the cutoff cancels.
Okay, no,
That's a true statement. Here I'm making a very strong statement, right? I'm saying that the whole operator part cancels, not just the dependence on the cutoff. So you're right. A useful way to think about this quantity is yeah, maybe it's worth writing this. This thing I call k delta. It's eta times delta hat plus 1 minus eta times I hat. Where by hat I just mean replace the entropy by k. And delta, so this is, yeah, KAB plus KBC minus KA minus KC. And similarly, this is, yeah. So indeed, each of these parts is nice in the sense that the cutoff dependence cancels, but only in the full combination does the whole operator part vanish. Yeah. Hyperbola.
Real-time picture, and then you do the conformal transformation to the imaginary time, and then you go to a circle, right? So the x1, x2 are on each circle.
I'm just think everything I'm talking about is at a fixed time. We don't ever need to talk about time evolution.
1 plus 1,
Yeah, 1 plus 1.
theory, right?
Yes.
Right, so then you get a circle. So that's one. So each Rindler observer goes into a circle in the region time.
Okay, that's true.
So x1 and x2 are in each circle or between circles?
I'm a little confused about the picture that you're describing, but maybe, it seems to me that the question you're asking me is about the derivation of this formula.
No, I understand that formula. I don't understand what is the meaning of x1 and x2.
Okay, so yeah, let's encapsulate the question of why it's true, and let me just tell you what the statement is. So yeah, my statement is that the entanglement Hamiltonian in the ground state of a 1 plus 1 dimensional conformal field theory, let's talk about on the line. If I specify an interval by 2 points, x1 and x2 are the endpoints, takes this form, where beta is this function. Yeah, we could talk about why it's true later. Yeah, but it's true. Okay, it's Ka is for one interval, each interval. Yeah, each interval. That's right. So here, yeah. Oh. Yeah, thank you, Marina. Yeah. This is a very important point, actually. This combination is it's a linear combination of single intervals, right? I never talk about the entanglement Hamiltonian of two intervals, which we don't know what it is. Yeah, that's right. Yeah, for free boson. For specific. Yeah, that's right. Yeah. So the entanglement. Yeah. Yeah. For two intervals, there's a whole lot more information. But the important point is that a single interval already knows about the Hamiltonian density. Yeah. Okay. So far, here's where I pay for my crimes. So far, I've been writing continuum formulae, right? Formulae they're somewhat dangerous in the sense that I said. I'd like, however, to compare. I'd like to study these quantities in a as I said, in a well-regularized realization of the CFT, an approximation to the CFT in a lattice model, like say some ground state of a quantum critical Hamiltonian on a chain of spins. Okay, and to do that, in order to compare, let me divide up the continuum, divide up the infinite line into a set of intervals, say equally spaced intervals, each of length a, and I'm going to regard each of those intervals as a site. This is a terrible thing to do, right? Each of the Hilbert space of this interval is infinite dimensional, right? I'm chopping up this continuum Hilbert space, but but in order to compare with a lattice model, I don't see any other way. Maybe there's some other way. Opposite. Yes, that's right. That's right. I agree. I agree. This is a different way of comparing the continuum with the lattice model. Yeah. Okay. So, and indeed, here's where I pay for my crimes. If I study this linear combination of entanglement Hamiltonians computed from the ground state of a quantum critical lattice model, that operator equation is not true. It's not true. And there's a simple way to understand why it's not true. It's okay. I guess in some people's language, it's the statement that in this finite dimensional Hilbert space, the state is not cyclic and separating. Right? Some people might like that language. That is, in a finite dimensional Hilbert space, think the reduced density matrix of rho A has the same eigenvalues, the same non-zero eigenvalues as the reduced density matrix of its complement. Right? We do some Schmidt decomposition. There's a set of Schmidt eigenvalues, but one of them can be bigger than the other one. Right? Generically, A and A bar have different sizes, and the spectrum of the bigger one is padded with zeros. Right? It's always padded with zeros. So notice that a zero in the spectrum of the reduced density matrix is very bad for the entanglement Hamiltonian, which is the logarithm of the reduced density matrix. Right? So log of 0 is minus infinity, and so, because of the fact that generically the reduced density matrix on the lattice always has some kernel, the entanglement Hamiltonian is a bit ill-defined, right? There's some parts of it that depend on UV garbage that we don't care about. However, when acting on the state that we started with the density matrix, the kernel of the density matrix completely disappears, right? That's what it means, right? Rho acting on the state is 0. And so acting on the state itself, the log of the density matrix is perfectly well defined. And in fact, this condition, which is just take the condition I wrote on the previous slide, which was an operator equation, an incredibly strong equation, n squared conditions on the components of the reduced density matrix if n is the dimension of the Hilbert space, which is not true in the lattice. This version of it actually is true. And it's still a very strong statement because, it's n conditions on the components of the wave function, of which there are n. And in fact, it should be true for every choice of regions A, B, C. And so it's, many more than n conditions on the n components of the wave function. So in fact, it's surprising that there are any solutions at all. And yet, the ground state of a continuum CFT, we know satisfies it. Okay, so here's some evidence that it's true. The error of this statement, so it looks like an eigenvalue equation. It's not quite but it's not a linear equation because the operator k depends on psi. Right? It's a very weird kind of equation. But nevertheless, the error of this equation, the extent to which this is violated, if it were true, the variance of the operator k acting on the state would vanish, right? Because the statement is when I act with k on this state, I get a C number. And so the variance of k delta evaluated in the state is a measure of the error. And as you can see, this is for the Ising model as a function of system size. You can see that the error decays like some power law in the system size. That's what I mean when I say that it's true. Okay, so I'm going to call that the vector fixed point equation for reasons that I'll explain. Vector is because it's a vector equation rather than an operator equation. And so, okay, I claimed that all of the universal information about the state of matter is encoded in the density matrix of the ball. But I didn't actually say what that universal information is. Right? In fact, I have to admit that I don't know what the universal information is. That's part of the question. Well, I don't mean the value. I mean even like what it is we should compute. Right? That's part of the question. However, there's a way to prove this statement without answering that question, which is if I can reconstruct from the reduced density matrix of the ball both the whole state as well as the Hamiltonian whose ground state it is, or let's say a Hamiltonian whose ground state it is, we can definitely extract all the universal information, right? If we know the Hamiltonian, like I said before, we know much more than all the universal information. We know lots of stuff that we don't even want to know. Okay, so let me show you that we can do this. So I said earlier that this Markov condition is it's a solution to the quantum marginal problem. That is, if you have reduced density matrices in A and B, which agree on B, then you can reconstruct the reduced density matrix of ABC. This fixed point equation, at least the operator version of it, is a generalization of that Markov condition. That is, so the equation that I wrote involves 3 sets of regions, right? It involves A and B and C in various combinations, and one of the terms is KABC, K of the whole thing. And if this equation that I wrote is true, so twiddle means subtract the constant part, it says that I can solve for the reduced density matrices of the whole thing in terms of the reduced density matrices of the parts. If I set eta to 0 in this equation, this is exactly the Markov condition. This is the condition for it to be a Markov chain. So this is a generalization of a quantum Markov chain in the sense that it's a family of conditions that allows us to solve the quantum marginal problem. Okay, so that's the evidence that we can reconstruct the whole state. What about the Hamiltonian? So just as we thought of these locally quadratic functions as a basis of functions on the line, and use them to add up to make the function 0, we can use them to make the function 1. If we do that, so that there is in fact a linear combination of them that adds up to 1, which I've illustrated here, which is just take the coolness function for 2 intervals and subtract the coolness function of 1 interval. So those things you can check add up to 1. And that means that if you add these, it's just equal to the coefficient of h in the integral is just 1, and the thing we get is exactly the Hamiltonian of the CFT. So this is again a continuum formula, but this object is extremely nice. It's in fact of the form of a delta hat in this sense, which is a very nice operator because so I said that delta non-negative is a version of strong subadditivity. But in fact, there's a strengthening of strong subadditivity, which is due to David Lin and Isaac Kim and collaborators, which is the statement that the operator delta, in this sense, is actually a positive operator. Whereas this is actually not positive. The other version is not as good. So in fact, yeah, weak monotonicity is sort of more correct than strong subadditivity in a sense. Okay. So that is this so-called reconstructed Hamiltonian is a positive operator, and we can check that if the state satisfies the vector fixed point equation, at least for enough regions, then it's a 0 energy eigenstate of the reconstructed Hamiltonian. Okay, so this is why I'm going to call this the reconstructed Hamiltonian from now on. Notice that it's a thing that acts only on 2 sites. It's a nearest neighbor Hamiltonian. And I should mention that there's a similar formula for the rest of the conformal generators by the same kind of tricks. And moreover, we can show that assuming the fixed point equation, the reconstructed Hamiltonian satisfies a scaling property. So that is, starting with the reconstructed Hamiltonian on coarse-grained sites, so like 4 sites and 2 sites, but using this fixed point equation, we can decompose those reduced density matrices into smaller parts and show that it satisfies a scaling relation with z equals 1. It's just a quantum information statement. Yeah. The proof in their paper assumes finite dimensional Hilbert spaces, but I think there's good reason. That's the explicit proof they gave, but I think it's also true more generally. Yeah, it's a very nice thing. Okay, so this is a picture. So this is some of the numerical data that I wanted to show of the spectrum of the Heisenberg chain on 8 sites, right? Very small spin chain, and there are 2 sets of data. One of them is just the spectrum of the original Hamiltonian that Heisenberg wrote. And the other one is the spectrum of this operator constructed from the ground state of that Hamiltonian. And you can see that they agree very well. And actually, one point I'd like to make is that you'll notice, so that the spectrum of a CFT on the circle tells us the list of operator dimensions, right? If we make the multiplicative normalization correct. And usually we do that by setting the dimension of the stress tensor equal to 2. You can see that I failed to do that here. The stress tensor is somewhere up here, and that's actually Heisenberg's fault. So this is just the, the normalization out of the box. But this condition here completely fixes the multiplicative normalization of our reconstructed Hamiltonian. And so I should have done this, but I didn't. If I had fixed the normalization not by Heisenberg, but by this, in fact, the stress tensor would have ended up at 2, and this would have been just the list of scaling dimensions. Okay. So here's a nice surprise. This vector fixed point equation, k delta on the state is some number times the state, is actually the condition for a particular linear combination of entropies to be extremized as a function of the state. Yes?
So you're saying that you have the density matrix of the ground state. You are reconstructing Hamiltonian.
Yes. Yes.
But this is, I suppose, it's true for relativistic theory because you know that you can reconstruct the theory. But for a lattice, you could change the spectrum of Hamiltonian without changing the ground state. That's what I don't understand.
How are you changing the Hamiltonian?
No, I mean, it's not clear for me that you cannot have the same ground state and different kind of
Good.
cyclic states.
Good. The extra information is that we're at the fixed point.
Okay, and where are you putting that?
Well, the conjecture is that this condition, this vector fixed point equation,
Okay, it's not completely exact.
So the statement that this is proportional to psi is a condition for psi to be the fixed point state. Yeah, implies. So this is a conjecture. Conjecture is an RG fixed point. So, if it's an RG fixed point, the whole you can't mess with the spectrum, right? And if it satisfies this condition, you can't mess with the reconstructed Hamiltonian. So I think it's, there's no freedom. Yes, please. Great. Okay, good. So, great question. So we can choose different lattice models that approximate the same CFT. Yes, I claim that if you start with the ground state of any of these lattice models, the Hamiltonian that I reconstruct in this way will be a better approximation to the ideal CFT in the given Hilbert space with a given range of the interactions. That's the statement. Okay. Okay, good. So Haldane-Shastry has tails, right? But that's the long range Hamiltonian. Yes. So good. So when I say best approximation with the given Hilbert space, I also mean fixing the range of the interactions. Yeah. So my Hamiltonian is always nearest neighbor Hamiltonian. If you want to study longer range interactions, you have to block the sites into larger sites. Yeah. So Haldane-Shastry is cheating. Yeah, that's not a local Hamiltonian. That's not allowed. Not allowed. Thank you, Paul. Okay. So the condition that I'm imposing is just the condition that the state is a saddle point of this function on the space of states, and the value of the function at the saddle point is the central charge times this function of eta. Here's a picture of this function in an example. And so here's the conjecture that I said, that critical points of this, extremal points of this function, saddle points, minima, maxima, are RG fixed points. And so here's an extreme implementation of this idea. So I said I was replacing each of these intervals in the continuum, this infinite dimensional Hilbert space with a finite dimensional Hilbert space. Here I'm gonna replace each of them with just a single qubit, right? So divide up the circle into four intervals and replace each of these with a single qubit. And this is a picture of the value of this function on the space of states of 4 qubits arranged in a chain that are translation invariant around the chain and time reversal invariant. That's an extra assumption. I'm just assuming the wave function is real. And here's a list of orbits of critical points. Orbits, I say orbits because this function that we're studying is invariant under local unitaries. So we don't care about the local unitaries. And in this list, in blue, you recognize some of our friends. So we identify a state that we associate with the Ising CFT, and 2 states that we associated with C equals 1 points. Notice that these are, one thing that's special about these particular CFTs is that they have a nearest neighbor Hamiltonian built on qubits, built on 2-state systems, each of them. And why do I associate these critical points with these CFTs? It's because given a state on these 4 qubits, I can reconstruct a Hamiltonian that's a local Hamiltonian, right? It acts only on 2 sites at a time. And then I can study that Hamiltonian on a larger circle, right? So I could study the spectrum of the Hamiltonian built from the same terms on a larger circle and just look at the spectrum. It's already normalized correctly and compare with the known spectra of these Hamiltonians. Actually, in the case of Heisenberg, the reconstructed Hamiltonian is the Heisenberg model. Great. So the central charge for Ising should be 1/2, and the central charge for these should be 1. Well, that's what we find, and one way to think about that is the quantity C that we compute this way. Actually, if you evaluate it in a particular limit of the sizes of the intervals, actually is the same as the information theoretic RG monotone that Marina and Horacio defined, and so it upper bounds the value of C. One question at a time. I'm not done answering your previous question. Okay. So in addition, so the approximation to C is not that great on 4 qubits, but I mean you have to admit it's only 4 qubits, right? It's okay. I can, but I'm not going to. So my goal here is to use very primitive tools, right, to learn what we can about CFT. So let me answer your second question. So you'll notice that this list also contains states that are not CFTs, that are not, or at least they're not infinite correlation like CFTs. So the rest of the states in this list are 0 correlation like fixed points of the normalization group. This ferromagnet is just the ground states. It's just the ground. There's no okay. Okay, let me explain a different example, which I think will be more illuminating. So there's one of the fixed points. When we reconstruct its Hamiltonian and study it on a longer chain, we find that the number of ground states on a chain of length L is the Elf-Lucas number, right? So it's exactly a local Hamiltonian that builds this Fibonacci chain that Paul talked about. So when I say it's a fixed point, I just mean it's a theory of the ground states. Uh-huh. The Hamiltonian is an output.
Okay, no, but you never use, say, I'm going to start with the Heisenberg and I can do something. So
No.
You just start with the state. So
Yeah.
you can ansatz
Yes.
for the...
Not even ansatz. We search in the space of all the states on 4 qubits.
So how do you
Yeah.
identify that you're saying this is Fibonacci?
Yeah.
Just because it has square root of 5s in it? Or
No, more than that. Yeah. So here, let me say the procedure again. We parameterize the space of states of 4 qubits, and then we do gradient descent on the variance of this k delta, right? So when that variance is 0, it means that the state satisfies the vector fixed point equation. And then we look at the minima, the places where that variance is as small as possible, and then and reconstruct from that state a local operator, right, which is k2 minus k1, the entanglement Hamiltonian for 2 sites minus the entanglement Hamiltonian for 1 site, and think of that as the local Hamiltonian density, which we can then study on a larger chain. And then we look at the spectrum on that larger chain. Yeah. That's the output. Yeah.
So in the 4th state, the 4 qubits,
Yes.
you get all, in principle, all the
all the ones that fit.
Oh, the fit, and then
Yes.
more, we be more precise and more fixed points and all that.
Right, so the ones we find on 4 qubits we can study as precisely as we want by studying a larger system. But as you can see, we don't find all of the CFTs. So then we study 3-state systems, right? Each of A, B, C, and D are three-state Hilbert space. And there's an analogous list that we're actually still compiling, which includes, in addition to these, also 2 more unitary minimal models and some more points along C equals 1, and then some states which we don't quite understand yet, with where the approximate value of C is bigger than 1. And the set of known CFTs with C bigger than 1 is somewhat sparse. There's actually a range between 1 and, I forget exactly what it is, maybe Herman knows it, it's 1.18 or something, is the next known CFT. And so I'm actually optimistic that we'll find something new, find some irrational CFTs. Yes?
That's why it came out this spin wave state, not the ferromagnetic state.
Okay. I guess maybe both of you are objecting to this word. You can see what the state is. Yes, indeed, it's a spin wave state. Yeah. You can teach me more about the ferromagnet later. I think that's maybe not the most interesting thing on this slide. So my conjecture is not that it's a CFT. It's the conjecture that it's an RG fixed point, which it is. Fiona has a question. Yeah, so the value of C is just, the value of S at the critical point is h of eta over 3 times C. Yeah. So if everything were exactly true, that would be C, but as you can see, it's an overestimate of C. Great. Yeah, so of course the problem becomes, so far we're just doing, everything exact diagonalization, right? Exact, storing the exact state and constructing these operators from it. We don't ever need to actually, so we actually need to construct the entanglement Hamiltonians as operators, right? Because we need to construct their spectra. So it's not just the entanglement Hamiltonian acting on the state, which is much easier. But so the difficulty grows pretty quickly as the local Hilbert space dimension grows. We can do the search probably for 5 state systems, 4 regions, each of which is a 5-state system. But already for 3-state systems, the bottleneck is that we've found a whole bunch of saddle points, and we need to identify them. And so far, we're doing that very manually. I think probably this summer we'll automate it a bit more. That's right. So for qubits, we find just the Ising model. For qtrits, we find also 3-state pots and tricritical Ising. Maybe some others. Maybe not. Yeah. Point 0.8. Oh, you're saying there are different modular invariants for the Potts model. Okay. Yes. That's a good question. Actually, I'm not sure. Yeah. Okay. I don't know. Yeah. We got one of them. We got at least one of them. Let me say that. Okay. I guess I'm out of time, so I should wrap up. Okay. Here are some practical comments about some ways in which you might use this. The final section, which I will not have time to talk about, is an attempt to generalize this strategy to 2+1 dimensions. We don't know an analog of the local vector fixed point equation, but we do have a guess for how to reconstruct the Hamiltonian. And maybe let me just point to one piece of numerical data. On the fuzzy sphere, we can approximate the ground state of the 2+1 Ising model using the fuzzy sphere following Yin Chen He. And here's a picture of the reconstructed spectrum using our attempt to reconstruct the Hamiltonian. The blue stars here are a 0-parameter fit. This is the analog of the output of the reconstructed Hamiltonian just from the ground state. So you can see that it's not perfect, but it's pretty good already for, I think this is for 10 orbitals. Okay, and so the conclusion, so okay. Same idea, yeah, same idea. Okay. Yeah, but the idea is, we perhaps we can find some new CFTs if you have an ansatz for the ground state of the Ising model, which Yinchen actually now does. Yinchen, he had a paper that came out last night with a analytic formula for the ground state of the fuzzy sphere transit field Ising model, which works pretty well, from which you could reconstruct the Hamiltonian using the procedure that I skipped and compare and see how well it does. Okay, so here's the central dogma again. It seems to be a pretty good idea. So far, we've implemented it to some extent in several classes of states. I think for any kind of phase of matter or a class of quantum system you might want to think about, you could ask this, the kinds of questions that we're asking. How, what is the condition on the state that it should satisfy, and use that to learn about it. Okay, and maybe the final comment is that it plays nicely with other versions of Bootstrap, of which there are many, and thanks for listening. Okay. Sorry for going over.